Hi there, and welcome to a kind of an introductory video to systems of linear equations. So there are all sorts of systems of equations that we can deal with. Some of them are what's called quadratic, which means there's an x squared, cubic, which means there's like an x cubed. There's square root systems of equations. Today we're kind of just starting out kind of the simplest we can get with linear equations. So, linear means if you were to graph a function like, let's say, y equals x plus 4. Okay, we know that the rise over run is 1, right? That's the slope. And we know the y-intercept is 4 here. So if we graphed it, we'd know this would be 4. And we would know that since it's just 1x plus 4, we know the rise over run is 1. So if we go to the right a unit distance, we'll also increase that same distance. So if this was 3, the increase would also be 3. That's that rise over run, right? So this is kind of your standard equation. What if we had something else like y equals, let's say, 3x minus 2? What does this look like? Well, if we plotted it on the same graph, it would the y-intercept would be at -2, right here, and the rise over run is 3. That's the slope there. So that means it's going to increase faster than the one we had before, and it's going to intersect with the other graph right here. So how could we figure out, without using graphing technology, where these two lines are going to intersect? Well, this is exactly what systems of equations will tell us. Okay, so if the important thing to remember is if we have two variables in an equation, we need two equations to solve it. So we could have three equations with three variables. We could have four equations with four variables. The main idea is that however many variables we have, that's how many equations we need to solve. So the first method I'm going to tell you how to solve systems of equations is called solving it by substitution. So whenever you're solving systems of equations by substitution, you want to isolate for one variable. So I kind of made it easy for you here. I isolated for y for both of these equations. Okay, so if you know that y is equal to x plus 4, right? We isolated for y. X plus 4 is the same as y, right? That's essentially what the equal sign means. It means that they're indistinguishable from each other. They're the exact same thing. So instead of writing y in the second equation, what can we write? Well, we know that x plus 4 is the exact same thing as y, right? Because we isolated for what y was. We know y is equal to x plus 4. So instead of y, I'm going to write x plus 4 equals 3x minus 2. Okay? And now, once we have this set up, it's just a matter of isolating for our variable here. So see how we only have one variable now? That's because we got it down to only one equation. So if we have one variable, we have one equation, that means that we can solve for that variable. So I'm just going to move this x, right? We subtract an x to the right, and we add 2 on both sides, right, to move this -2 over to the left. This x is going to go away. These 2's are going to go away, so we get 4 plus 2, that's 6. 6 equals 3x minus x. It's going to give us 2x. And the last step we got here is just dividing by 2, right, to cancel this 2. So we've effectively solved for x. So 3 equals x, and that basically means on our graph up here, see before where I drew the intersection here, that means that where they intersect, our x value is going to be 3. Okay, and now that we know that, we can also figure out this y value. Okay, so the hardest part is figuring out one of the variables, but once you have one of the variables, actually, hold on, I'll only cut this out here. Once you have one of the variables, it's a lot easier to find the other one. So to verify your solution, you always kind of pick the easiest looking equation. So in my mind, this one looks a bit easier. So if I know y equals x plus 4, right, how could I find this corresponding y value when x is 3? Well, for both of these equations, y is going to be equal to x plus 4 or 3x minus 2. Both of them will work. We're using x plus 4. So the y value, this kind of unknown value right here, is going to be our x value, which is 3 plus 4. equals 7. Okay, so this value right here is going to be 7. So the point of intersection for these two lines is going to be 3 and 7. And just to kind of prove it doesn't matter which equation you use, we can use this second one right here. So we know y equals 3x minus 2. What is x? Well, x is 3. So we get 3 times 3. What's that? That's 9 minus 2, right? And that is also 7. So you know if your system of equations, your system of equations is right if you plug in the same x value and you get out the same y value. So that's kind of where they intersect right there. That's just sort of an introductory type question. So here's one you might see in your textbooks or on a test. Consider the following system of equations. Okay, so we know x plus y equals 24. 2x minus y equals negative 6. What's the value of x? Confirm algebraically. Okay, so when they say confirm algebraically, that just means do what we did up here, is figure out what x is and make sure it works for both equations. Okay, we don't need to figure out what x is, we can figure out what y is. We just have to kind of isolate for one of them. So I've only shown you solving it by substitution. So let's kind of continue that theme. Typically, when I work with people with these kinds of questions, I ask them, I say, do you want to isolate for x or do you want to isolate for y? Because it really doesn't matter. You're going to find the same answer either way. So typically, I like to isolate for y, just because I like to see y equals, but it doesn't really matter. So if we isolate for y, right, we have x plus y equals 24. What do we need to do to just get y? Well, we can just subtract x. So we know y equals 24 minus x. Okay, and we got 2x minus y equals negative 6. Okay, we don't need to isolate for y for both equations, just for one of them. And now that we know y is exactly identical to 24 minus x, instead of writing y in the second equation, you guessed it, we can just write 24 minus x like we did in the last one. So remember, when we subtract y, we're subtracting all of y, all of this quantity. And lots of people mess up here. They just put, they forget to put the brackets here and they just write minus 24 minus x. That's not what we're doing. We're subtracting all of 24 minus x. So remember that negative has to distribute into both of these numbers here. Okay, that's super important. So 2x minus 24, people get that part, but they forget this negative and negative makes a positive. So remember, we're adding x and that equals negative 6 over here. All right, so once we have this, we're just kind of isolating for x here. So we have 2x and x that are adding together, right? So those are like terms, so we get 3x. Right, and then we want to move our numbers, our constants, to the other side. So we add 24, negative 6 plus 24, that's positive 18, right? And then we just want to get x on its own here. So we divide by 3, 18 over 3. Pop quiz, that is 6. Okay, so if we were to draw both of these linear functions, right, these lines on a graph, that means that they would intersect at x equals 6. I'm not going to draw it out, but I kind of illustrated that in the last example. Hopefully it kind of makes a bit of sense. So now that we know x equals 6, how can we figure out what y is? Well, remember what I said before, to verify it, to kind of figure out what y is, we take the simplest looking function and we just plug in our known value. Okay, so I think x plus y equals 24 is the easiest looking one. So x plus y equals 24, right? We know x is 6, so we can say 6 plus y equals 24. Right, just a little bit of algebra here, minus 6, so y equals 18. Okay, so the point of intersection is 6 and 18. If you were to graph it, I'm not quite sure what it would look like, but I do know that it would intersect at the point 6 and 18. So it could look, kind of like this, right? It could cross there. It could look like this. So if you were to graph both of them, that's where they would intersect there.